Hey everyone, this will be a review of some of the challenges at X-MAS CTF 2022. It was a CTF hosted by HTSP and it was a 5-day CTF. Overall, a lot of fun. I definitely learned a lot. So in this video, I'm going to be covering the solutions to the challenges I solved. It was about 15 of them. The solutions are going to be pretty quick and dirty. Basically, I just want to talk about the ideas. I'm not going into too much depth on any of them. The first challenge was Santa's Complaint Hotline. You can see it's only 50 points, which means that a lot of people solved it. There's the description. We're given some files. So we have the individual, the challenge file, the actual binary. We have the linker loader, libc. Off the bat, we can see it's 2.27, which is nice if we're doing heap exploitation, but we're not doing heap exploitation for this challenge. First thing first, we load up Ghidra. It's not loaded, so we're going to load Ghidra in the background. Over here, I just have a Docker container running Ubuntu, so we can take a look at the challenge. So the challenge, when we run it, it says, write all your complaints you have about Santa. They will be merely redirected to dev null. Not much actually happens. If we run checksec, file is equal to chal, we can see we have partial row, so we can overwrite the got. We have no stack canary, which means we're probably going to be doing a stack overflow. NX is enabled, so we're not going to be injecting shellcode. We're going to be doing, we're going to be wrapping. No pi, so we can jump back to an address within the binary itself. So this could be a ret to win, or if we're wrapping, we can jump back to some address we control. Cool, let's take a look at Ghidra. Cool. If we look at the functions, it's not stripped, so we do have main. And taking a look, we can see it opens up dev null. Then I'll just rename that. Null, it does some buffer stuff. We can see the puts call, where all the complaints you have about Santa, they will be merely redirected to dev null. We enter a while loop. It's going to do a compare with this data here. We can see it just says done. We can change this to C type. Or C-terminated string, so it's going to compare with the word done. If it is done, it's going to return. Otherwise, we're going to do a memset, fgets, and fwrite. So first, we're going to memset some buffer. This looks like our in buffer. So we're going to read 0x200 bytes into the in buffer. So this is 512 bytes, and then we're going to write the in buffer into the null file pointer 1 byte at a time for 512 bytes. So at this point, when I saw this, I was a little bit confused. We can see we're only dealing with 512 bytes at a time, but it's defined up here to be an entire kilobyte, which makes it kind of hard to do a buffer overflow. And I looked at Ghidra really quick, and it does look like the offsets are pretty high. So I'm not really sure how a buffer overflow is possible, but there also just isn't that much else we can try, so at this point in the competition, I just went and tried a buffer overflow and it worked. If anyone else did any digging and saw how that worked, that'd be nice to know, because I'm not too sure, but I haven't really dug into it. Anyways, so most likely it's a buffer overflow. We can check this pretty quickly. What we're going to do is, this is our solve script, so we're just importing pwn, we're loading the library. It's chow patched. There's a tool called pwn in it, which you can use to load in the libc and the linker library, and so it kind of matches the remote system. Do some context setting, starting the process, do a quick sleep. We're going to attach the JDB. So this is what I do just to make sure it is a buffer overflow. We're going to do a pwn cyclic and send 2000 bytes, and this should overwrite the stack, and that way we know we actually do have a buffer overflow. So we can write it, double check. We're going to do Python 3 solve, JDB is loading. Oops. Little typo. So JDB started, we're running the program on the left. We do continue, and we can see, yes, the return address that's being popped off the stack looks like ASCII. So it is a buffer overflow, and from here we can start wrapping. So the overall goal is, we know we can wrap. There isn't that much in the binary, and so what we're going to do is we're going to try to leak the address of libc, and then from there we can do a one gadget and jump back to main, then redo the buffer overflow and jump to that one gadget. And if you're not familiar with one gadget, very nifty tool. Basically, it'll find a gadget an address within libc that will spawn shell, which is absolutely amazing. So we can see at this address, it'll call execCVE, bin shell, as long as these constraints are met. And for this specific challenge, it was I got the second one to work, so that's the one I used. But let's take a look at the script. All pretty standard stuff. So we're going to be ropping using the Pwn tools rop. First thing we're going to do is, sorry, let me back up. So we did a Pwn cyclic. We were able to show that there was an offset. You can then use Pwn cyclic find with the string that generated the offset, and that ended up being at 1037. So from there, we know that the bytes that come after 100 or 1038 bytes is where that address is going to be popped off the stack and set to RIP. So we can start executing there. So then we're going to start our ROP shellcode there. Sorry, just our ROP code, not ROP shellcode. Our ROP code, and what we're going to do is leak the address of puts so that we know where libc is. So we're going to call puts with the GOT entry for puts. We know that the GOT has already resolved puts because it calls puts earlier, and then we're going to jump back to the main function so that we can do this again. So we build out that payload, we send 1038 bytes of just A, then our ROP payload, and then we send done. I don't think that's necessary, but maybe I'm misremembering. Anyways, we receive some garbage bytes, then we get the leak for libc, which is just the address of puts. We calculate the address of puts, and then from there we can calculate the offset to the base of libc. Then we eat up some garbage. Cool, then we can send our next payload. So at this point we're back at the top of main. So we're back up here, and we get to do the exploit all over again. So we're going to do our buffer overflow, but this time we're going to jump instead directly to the one gadget. And this is the one gadget address we found on the side. And after that we should just get shell. So we can try, see if it's still working. Sweet. Oh, we're not in a terminal, so we can't clear, but you can see at this point we do have shell, which is just running locally. Cool. So that was that challenge. 50 points. You can see a lot. The next challenge was naughty list. We have some challenge text. We're given some files and a netcat. And the file is just a single CPP file, or C++ file. So let's take a look. So we are given the C++ file. Let's actually run the binary first. We have three options when we run. We can ask for the flag, we can query the naughty list, and we can add to the naughty list. So if we ask for the flag, it prints out Pinkie Pie, and it says Pinkie Pie will not tell you the flag if he is on the naughty list. We can query the naughty list. We can see this name is not on the naughty list, but if we ask for Pinkie Pie, we can see Pinkie Pie is naughty. And then last, we can add names to the naughty list. So we'll add ABC, we'll query, we'll see ABC is now on the naughty list, and if we ask Pinkie for the flag, we can see the name ABC and Pinkie Pie, but Pinkie Pie will not tell us the flag if he is on the naughty list. Cool, so we have a rough idea of what the binary is doing. Let's take a look at the code. If we scroll all the way down, pretty small file, we can see there's a main. It's going to print out a menu, it's going to read in a choice. Depending on the choice, it'll either ask Pinkie something, or for 2 and 3, which is query and add to naughty list, it'll read in a name, it'll see if it's naughty, or it'll add a name to the list. Cool. And so our goal is to print out the flag, and Pinkie said something about this. Pinkie said, will not tell you the flag if he is on the naughty list. So if Pinkie Pie is not on the naughty list, we can see it's printing out the flag here. So cool. So we have 3 different options from the menu, and we have 3 different functions up here, plus the menu. So we can add to list, is naughty, ask Pinkie Pie, and somehow within ask Pinkie Pie, it prints out the flag for us. Checking out anything else before we dig into those functions, we can see up here there is a naughty list. The naughty list starts out with just one person, which is Pinkie Pie, so I'm guessing this is the naughty list that Pinkie Pie was talking about. We can also see that there's some max count of 16, and that seems to be it. So we can look at the 2 smaller functions first. First is add to list. while the list size is not equal to 16, we can add people, and it's just a raw insert. And naughty list was a unordered map. So we can keep adding people to this unordered list or unordered map until there's 16 of them. Is naughty is just gonna read this map and see if a name is exist. And so all we have left is this last function. This is the function that prints the flag, so we can just work backwards and see what conditions need to be met. So to print the flag, Pinkie Pie must not be naughty, and we can see this is set to false initially, so somewhere in here it's being set to true, and it's being set true when for I and 16, it's going to look at the iterator, so the naughty list, and it's going to check and see if Pinkie Pie is a member of the iterator, so, and if it is, Pinkie Pie naughty will be set to true. So it seems like at first glance this shouldn't be possible because we can only add 16 people to the list, and this function is going to iterate over all 16 members, and Pinkie Pie will then always be a member of the list. When I first saw this challenge, I figured it might be some sort of hashed collision, because under the hood, maps usually hash maps, and so maybe we could force a hash collision on this unordered map, and maybe it'll report the size incorrectly, or maybe there'll be some confusion and Pinkie Pie can go missing on a hash map. Seemed unlikely, but eventually, after much playing, I couldn't get that to work. I was playing with this, and I realized simply by querying a name on a unordered map, it'll actually create an entry. And so what you can do is just query a bunch of fake names, and if you query like 200 names, the chance that Pinkie will pop up while iterating over everything because it's an unordered map is pretty low. So to get the flag really isn't too bad. All you have to do is query, 100 names that don't exist, and from there you can call the ask Pinkie Pie, and chances are pretty high that Pinkie Pie will not be one of the first 16 returned, and the flag will be printed. So I have a solve script for it. Nothing too exciting. It basically just does that. Does pwn tools. It'll ask for the flag. It'll query. These are the scripts for the three options: ask, flag, query, and add. And then from there, I just add a bunch of names. I query 200 times with a bunch of fake names, and then I ask for the flag. So overall, pretty simple and fun challenge. I did not know that about ordered maps or unordered maps. The next challenge was Krampus Greetings. 438 points, so it means a number of people solved it. Looks like 37 people solved it. We're given a description, and we're given main.cpp, a main, and a netcat port. So we can go over here. Let's take a look and see what it does. Make Ubuntu. And we will run it. So please enter a pattern character. We're going to say A. Enter a number of symbols. This part was a little bit confusing. I'm kind of cheating. We'll just do AAA. Enter the greeting. Hi there. And we can see it prints out AAA. Hi there. AAA. So let's take a look at the code. Cool. Right off the bat, we can see we get this flag function. So it looks like we have some sort of ret to win competition. Let's actually do a check sec. We can see no partial rel row, there's no canary, so we do have an overflow, no shellcode, and we can do a very simple ret to win if we can overflow the stack, which most likely if there's no canary, we probably will be doing that. So we have a ret to win, and we need to jump to flag. If we see there's only two functions, there's main and generate greeting. In main, we can see we have the same sort of thing we were doing over here, enter pattern character. It's going to read a single character, enter a number of symbols. It's going to read 512 bytes, but if you actually go through this code, it's a little bit strange, but basically what it's going to do is it's going to calculate this pattern count, and that's the whole goal of this code. You can see when we call the next function with the symbol, so the initial symbol and this pattern count. And basically what's going to happen is through some stuff, it's going to see how many occurrences of this symbol, these letters occur, and calculate that number, which is pattern count. And then from there, that's going to calculate how many of these A's are above and below our greeting. But skipping over that code, we can see we have a buffer here. It's going to be initialized to 0, and it's 2312 bytes long. So this looks like probably our buffer overflow target. If you go through the math, like I said, it's a little bit weird how this actually gets generated. You can see it's generating powers. If you go through and you can see it has an initial size of 1, 2, 3, 4, 5, 6, I think it generates something like 1,000 bytes roughly, a little bit over 1,000 bytes. 1,000 will be passed to this. And so what that means is you're going to set 1,000 characters here to output, and then an extra byte for the new line. And then here it's going to enter a greeting, and you get 1 to 128 bytes that you get to add to this output cursor, to the cursor, which will then eventually be set to output. And then we get to add the little bottom part of our greeting, which will be another 1,000 bytes. And then we're going to terminate it. And that ends up, I think, being exactly 2,312 bytes. So at first look, this doesn't look possible for an overflow, but the whole trick behind the program, or this challenge, was there's 6 characters here. There's actually a null byte character here, which we can't see. And so, again, if you actually just read through this code, you'll see that you're actually able to generate a pattern count that's larger than intended. And from that, you can generate a buffer overflow within this output buffer. Specifically this read, so you're going to generate a very large buffer here, and then you'll be able to just inject your ret to win. So if we look at the actual solve script, really wasn't too bad. We connect, we do some setup, load the binary, we connect, we read the characters, we send a line. This is the line we do to generate a very large character count. We're going to receive until greetings. We have our ret address. I just got this from Ghidra. So this is an address to something that just calls ret. I think there was a stack alignment issue the very first time I ran this, because we're calling bin shell system, and so sometimes on newer versions of Ubuntu, newer versions of libc, there's a stack alignment issue, so you just put in an extra ret in there, which we can see right here. We have our win address and main. For some reason the binary wasn't working at first when the exploit wasn't working when I connected remotely, but I was able to get main to work, and I think there was just a bug somewhere in my script, but I use that to verify. We don't actually need that anymore. So for the actual exploit, what we're doing is I'm sending a null. I think this was necessary to not clobber something. I don't quite remember, but we use this to not clobber. We're going to send some filler. Basically, I just run the exploit a couple of times and then look in GDB to see what I need to do, because I tried to solve these pretty quickly, and I saw that this combination worked. Then we're going to do our ret address just to get the stack alignment to work, and then from here we can do our ret to win. I just sleep for a second, and then from there we have shell. So overall, pretty simple challenge. And you can see we get the flag. The next challenge is Krampus Gifts. We can see he's given us access to his gift management platform, and he's asked us to investigate it. We're given the linker loader, libc, pthread. As soon as we see pthread on a competition, we know it's probably some sort of timing attack, and we're given the binary and a netcat port. So let's take a look. I have the challenge here. If we run it, we can see welcome to Santa's Gifts. Please note it's a very busy time, and our requests might take a while to be accepted. Cool, so we can request a gift. I'm going to request a gift at index 0. I'm going to say ABC 1, 2, 3. Cool, we can view the gifts. We can see the gift we just added is here. We can edit the gift, so edit at gift 0. We're going to say ABC 1, 2, 3, a bunch of exclamation points. We can view the gifts again. We can see the edit took place, and we can reject the gift. We give it gift 0 or index 0, and if we look at the gifts now, we can see it no longer exists. So this is very much looking like a heap exploit sort of thing, along with a timing condition, timing attack. Anyways, let's take a look in Ghidra. So we have the code here. So we have our main loop. We can see the puts call looks very similar to what we saw. We can see it's reading in. It's doing a switch case with a bunch of events. We can either exit, so that it looks like there was a hidden option that we didn't see. We can add, view, edit, or delete. If we look at the add code, we can see it's going to ask us for an index. It's going to read the index, ask for a name. It's going to call a malloc with OX 70 bytes. It's going to read that in, and it'll terminate it. Then it's going to spawn a thread, so that's interesting. and it's going to do an asynchronous add. We can see when it's adding, it's going to sleep for a second. It's going to do some sort of checks. It looks like there's a global array of gifts, so it's probably going to save. We're only allowed to have 10 gifts, and it looks like it saves that into the data section, and so this is probably a list of pointers to our mallocked gifts. It's going to do another malloc, and that's going to schedule event, and the event will do another malloc, go into that gifts array, assign it, do a string copy, and then eventually free some stuff. So if you go through all the functions, you're going to see that there's different conditions for when the events happen. So like if we look at edit, it's going to do the same sort of stuff. It's going to ask us for an index, it's going to malloc, then it's going to do this spawn thread async edit. And within this, you'll see it'll do some sanity checks, and then it'll sleep for a second. Whereas in the add, it was sleeping for a second and then doing the sanity checks, and then the actual event happens. The actual event doesn't actually happen until resolve events occurs, which is interesting. So things get added onto a stack, and then there's another thread, like a job queue, and then there's another thread that actually executes the jobs. But jumping to the solution, usually when it comes to these challenges, I try to keep things pretty quick, which usually just means dirty, and I just try to get something to stick, and once it sticks, I exploit it. So we're looking at the solve script now. Nothing too special. We're importing pwn. We have our binary, we're loading it, setting some context. We're going to spawn the process. We have the different functions for the different actions we could take. So we can request a gift, we can view gifts, we can edit gifts, and we can delete gifts. I stored some addresses. If you keep investigating, you'll see that there's actually a win address. We can take a look. So there's, within the binary, they were nice enough to provide us this. So there's a function, a ret to win, with system bin shell. So the goal is to jump there. We have a gifts address, so this was the array within the data section. You can see it's the address is a little bit higher. And so this is the array of pointers to mallocked gifts. I also recorded the address of a GOT entries. I just recorded free. I don't think we're exploiting free. There's one that's maybe 2 elements past free. We'll take a quick look in GDB that I ended up exploiting. So this one was just before. And then a little test adder. So for these challenges, usually I just, you can spend a lot of time reversing it, or you can just try a couple different things and see if something sticks, which is usually what I did and what I did for this challenge. So I just requested a bunch of gifts, I sleep for some time, I delete some gifts, I request another gift, I sleep, I edit a gift, and what we're trying to do is we're trying to have a gift, kind of a use after free. We want the gift to go back onto a malloc bin, so either the fast bins or the thread bins, the tcache bins, and we want it to have it be on that list. So we want to overwrite one of the forward pointers with an address we control. And specifically, we're going to try to overwrite it with the global offset table. And so that way we can then edit the global offset table. And next time one of those entries, one of the libc functions is called, we can replace it with something we control, like the ret to win, and then the binary is pwned. So basically I just kind of like I said, I'm going to request a bunch of gifts, delete them. Then while that deletion is happening, we're going to edit it real quick. After the deletion happens, so we're kind of using after free. We're going to try to overwrite the forward pointer with GOT, the GOT address. Then we'll request another gift. I do some extra stuff in here. I think I'm just aligning the heap correctly, because there's a bunch of things that call heap with the same size. So I think that was just necessary to kind of align. Eventually, we're going to request another gift, and we're going to do our win address. We just put it in there a bunch of times, and so this will overwrite the GOT with a bunch of entries. Actually, so if we back up, we're going to request a gift 0, and the way the heap bins are aligned, it's going to return us a chunk that's actually at GOT. And so then when we edit this one, specific one, I think we could actually put the win address here. Actually, I think the binary got upset when you did that. So I think instead it was easier if we just put A's in there. So we just edit it after the fact and put the win address in there, and eventually one of the GOT functions will be called, and it'll just jump to win. We can take a look in GDB to see what this actually looks like. Python 3, solve. So I'm going through the process of just creating and deleting different chunks on the heap. If we look at what bins we have here, we can see some fun stuff. So we're looking at T-cache bins. We can see for this size, we have a chunk, but the next chunk's forward pointer points to the GOT, which is exactly what we want. And so that means we can ask for a chunk, and then the next chunk will actually not be where it's supposed to be, and we can start overwriting stuff on the GOT, and because of that, the next time we call libc function, we can put in our win function, and we win. And so I think that should work. If we continue, oops, sorry, I think I need to get rid of that. I think we broke GDB. It's calling, it's aligning, and eventually we're able to return to that ret to win, and we get shell. So pretty cool, fun challenge. The next challenge was Lapland Beacon. Another very interesting challenge, 490 points. We're given a couple of files, a single file, just the binary, and a netcat port. So for this challenge, let me go to it. Is it beacon? Make Ubuntu. I played with it for a while. If you load it up in, actually we'll do that correctly. Beacon. Load it up in beacon in the background. If you play with the binary, we'll see not much actually happens. We get unknown command. Eventually we're going to find this command. Was it health? Nope. It must be at a weird offset. There we go. Health. It's pretty pog, not going to lie. But there's not much else going on. So we definitely need to reverse it. We can call strace, which is eventually how I found the solution. We can see what it's doing. It's reading a flag, which is super interesting. So we know it's reading the flag. It's also opening up dev null, and it's waiting. We saw that health did something. So when we call health, it's reading from standard in, which is now 3, and then it's writing to 7, which is now standard out. So up here, the file descriptors must have been mapped, which is different. And somewhere also important, yeah, it's also opening up dev null, and so this is file pointer 9 now, which will be important in a second. So Ghidra's slowly loading. It's taking its time. Cool. We have the binary. We got a start. We got a main. Always nice to have a main. We can see it's using a bunch of boost stuff. That's a bummer, which looks really nasty. I'm not sure if there's a way to clean it up. If anyone knows, that'd be great. But we're just gonna search. We saw that health worked. If you can manually go through it, and eventually you'll find these strings. But health. The very first time I had to find the strings, I couldn't find them. We're gonna look at xref. Already we can see that there's something up above, broad C, which is interesting. Parse HTTP request. We can take a look and see where it's being used. Again, the code looks pretty nasty when you read it like this. So to actually solve it, what I did is I tried to play around with that for a while. I had a rough idea what was understanding, but I started calling, actually let me run the binary by itself. What was it, main? Oh, beacon. So we saw health. We also saw broad C, which doesn't do anything. So when I ran it in strace, beacon, so we got health, and it responds with pretty pog, not gonna lie, but when I do broad C, we can see, where is it? Broad C. Did I type it wrong? I'm doing something wrong. Oh, I think I know what it is actually. I'm going a little bit too fast. There was probably an error up there that I did not pay attention to. So we can see the flag is normally defined to be at root. So, and I don't have one right now. So let's just generate a fake flag. Hi world. Cool. Now if we run strace, oops, beacon, and we do broad C, there we go. I must have missed that. So you can see it's opening up the flag, and then now when you call broad C, it's actually writing the flag to file pointer 9, which we saw earlier up here is dev null. So when you call broad C, it just writes it to dev null. So at this time I went back to Ghidra and I looked all over the place to see if there was anything exciting, and the only thing it's really doing is reading 6 bytes at a time and then executing the code. So I tried a bunch of stuff, and eventually I started messing around with just stringing together a bunch of commands at the same time, and what you'll see is sometimes they get pushed together. So right now it actually just happened here. So write 7, so we're writing the standard out, health, pretty pog, not gonna lie, with the flag appended. And so what's going under the hood is it's asynchronously adding to this buffer, and the buffer isn't always flushed, is my understanding of what's happening. And so you can put a bunch of stuff on a buffer and then it gets flushed eventually, and if you're lucky it'll be flushed onto standard out instead of dev null. So I think what we did, health, broad C, health, broad C, oh it is wrong, OD, broad C, health, something like this, and you can see the flag actually just prints out. And I was pretty surprised that this was the solution. I think this is the intended solution. Didn't copy. And we can try it here. Health, broad C, health, broad C. And we can see we get the flag just like that. So pretty fun challenge, very different. Not an exploit I've seen before, but yeah, it was cool. The next set of challenges were the blockchain challenges. There were 3 of them. I don't have much experience with writing Ethereum contracts, so the hardest part of this for me was just getting everything set up and trying to understand what you're supposed to do. But if you know what you're doing, these challenges were actually super simple. So let's look at the first one. So in the first one, let's look at the description. There's a bunch of stuff. I don't think there was a hint. It doesn't look like it. Yeah, I don't think the description gave us much. So if we look at the files given, we're given 1 blocker, Solidity contract, and we're giving a netcat port. So let's check out the netcat port, see what it does. It'll launch an instance, kill an instance, or get flag. So if we launch an instance, we're going to get a UUID, an RPC endpoint. So this is probably a private Ethereum network. We're going to get a private key, presumably loaded with some gas already, so that we don't have to mine or go to one of those faucets. We don't have to pay the gas fee every time, or we're given funds for the gas. And then there's also a setup contract. So like I said, the hardest part of this was actually just figuring out what we were supposed to be doing. I thought at first the setup contract was the Solidity one that was given to us. So we were given this script. It turns out this actually points to a different contract. And that other contract then calls this one. And like I said, this took me quite a few hours to actually figure out. The trick was to take this, and we're going to dump the code at this contract and see what it's doing. And so we can do this. Let me update these values. So we need an RPC endpoint. Here, we need a private key. Here, we need a setup contract. This one, this only lives for 30 minutes, which is why we have to keep recreating it. And somewhere I call code, or I dump the code. Here, let's take this out, and we'll just put it here, and we'll do embed. And this should be a... Alright, so we're going to do a couple of different things for these challenges. I just print a bunch of stuff out because I don't really know what I'm doing. So we're given that private key. So using Python Web 3, which is apparently a very standard library, we can load the account. I'm just seeing what's in this account. We can see we have the address, and it gives us a balance. And I think it has a pretty large balance, so we have more than enough gas than we need. I don't quite understand this. I think maybe by default within RPC you have some accounts already. So when we call web3f accounts, so sorry, backing up, we connected to the RPC handler using this code here. And so we have this RPC web3 handler. When we ask what accounts we have, it looks like we're also given 3 accounts here. Again, I'm not really sure what that's about. Or sorry, we get 2 accounts here. And yeah, actually, let's run this up here. The rest we'll figure out in a second. So first we want to see what this setup contract is. Python 3. Oh. Didn't like it. Data did not match. Something's not right. DB56. We have the primary key. We have this. I'm not gonna try to debug it, but basically we're gonna get the code here. Oh, this is get block. We want code. Oh. I was debugging that, I guess. Sorry, it was a get block call instead of a setup contract. And we actually want to call hex on this. Oops. Ignore that, we'll just do it manually. Cool, so this is the Ethereum contract code that's being run. So we can go to, I think I put the address up here, to a decompiler, ethereal VM, this one. We can put in this raw code, decompile, and so this is like the Ethereum assembly equivalent, I guess. I think this is pretty much the best you can do. So you just kind of read over the code. Eventually what you'll kind of see is it's loading this address from var1, and it's making some sort of call on it. And so I figured this address is probably important, var1. And if you look at where var1 is loaded from, it's loaded from storage var0, which is 0. So it turns out you can dump the storage of a contract, which is what I ended up doing. So, so this is where we loaded the code. You can then say web3 Ethereum get the storage at this contract, and I want the first value at this contract. And this actually happens to be the address of the Solidity file we were given. So I guess the challenge author, what they do is they run this setup contract. This setup contract then creates an instance of our actual challenge script. So we need to get the challenge contract from here, and we can find that because it's the first value in storage. Cool. So what we're going to do is we're going to read that first value from storage. I got a little bit smarter as I went through all the challenges. You can actually just do hex here. We get that address. For some reason we have to convert it to a checksum address. I think sometimes you see the addresses both lowercase and uppercase, and somehow that's some sort of checksum. I don't quite understand, but if we make this call, things work out. Cool, then we need to compile the Solidity. So to interact with a contract, you need to have the ABI, Application Binary Interface, for that specific contract, which is why we don't have the source code for the setup contract, which is why we had to go to the decompiler. But for our actual challenge, we have the code. And so we can compile it using Solidity, and from there we can start interacting with the contract because we have both its ABI and we have its address. So let's actually take a look at the code and our challenge. We can see that there's some sort of solve function and a get previous time. It's going to see if it's solved, and otherwise a pretty simple contract. I think thankfully other people in chat were talking about this, and I think it was kind of leaked or implied that your goal is just to get solved to be true, And when it's true, the checker script will then check this function, and you'll get the flag from that initial netcat that we did to set up the challenge. And so to get this to be equals true, we need to call this function with a guess parameter that's equal to the previous timestamp. And the previous timestamp is just block.timestamp. Cool. So to do this, I'm not really sure if this is when, at first I wasn't really sure when this was created or if this was like the previous instance of when it was run. Because I think there's also a self keyword or something like that. So maybe not. So what I did instead is I just put it in a for loop. Where is it? Sorry, so we compiled the, wrong one. We compiled the SOL, we created an instance so we can now interact with that contract with the address and the ABI. I just print out to see how many transactions this address has taken place with, and just to make sure everything's working correctly, and I think it prints out 1. We can see at first I thought it was the Genesis timestamp or the timestamp of when it was created, but that is not the case, but I print that out anyways. At this point, I pretty much just run the script a bunch of times and see if I can just get lucky. I figured it was when the event was happening and maybe there was some sort of clock skew or something like that. So basically I just do from -10 to 10. I say the time's equal to current time plus that offset. And yeah, I just try to solve it. I think at -3 it worked correctly. But anyways, you call the function. I say from where. This was the address that was given to us. I give it some gas. Then you don't automatically, you have to wait until the block is mined, I think, before the code is actually run. So you get a transaction hash, and so then you just wait until the event actually happens, and then from there, you can look at the receipt of that transaction, and if the status is equal to 1, the code was successful and it ran. At this point I just say, whoa, and the rest we can ignore. That was just debugging stuff. So once you run this code, you can then go back to that netcat. Oops. Well, status was 1, so maybe it did work. We'll go to netcat, and then you just do get flag. You give it the UUID it gave you, you give it the contract script, and then it'll print back the flag. So like I said, the hard part was just setting up. It's all you had to do is just give it the timestamp, and then you get the flag. So really not too hard of a challenge once you're set up. For the second one, it was called Cookie Market. It says retrieve the hint, retrieve the OG, so the original cookie to get the flag. We're given some files. This time we're given 2 Solidity contracts. And we can take a look at them. So we're given this cookie. It says some sort of like object-oriented programming. It's based on this ERC 721. If you Google that, you can see it's like a known cookie standard. Open standard that describes how non-fungible or unique tokens. So we have they're unique, non-fungibles. So that's I think there was a different word for them. I'm blanking on for the second. Anyways, and so we're given these 2 pieces of code to be able to. It has to import this stuff. I ended up finding these Solidity files somewhere on GitHub. It was called Open Zeppelin. So I git cloned Open Zeppelin, and then I copied some files to the top. But these files import some other stuff that they locally, so I had to change these imports to get everything to work correctly, but eventually everything worked correctly. Just getting the imports. I'll just go through them real quick. So I had to change these so that it resolved correctly. But anyways, we have these 2 files. So we have a cookie, it's just called cookie. It has a cookie ID and owner. Looks like you can mint a cookie. The initial cookie is called 0. And when you mint it, it's asking for the address of the sender and a cookie ID. So it looks like it said we wanted the OG cookie, so we probably want cookie with index equals to 0. So we come back over here. This is the cookie market. So we have a mapping, so just a map from a number to the address. So we can see who can redeem the cookie. So maybe this will be a cookie 0 belongs to the address of the owner or something like that. There's a market, so I'm guessing this is like a buying and selling market. The cookie ID, how much Ethereum, the provider, a list of sell orders. This is the cookie, and it's set in the constructor. So when you create a cookie market, you pass in the address of some type of cookie, and it saves that cookie structure. Cool. So that means somewhere in this contract, when it's deployed, it'll have this in its storage, which we can use to verify stuff. Anyways, there's a constructor. There's some stuff to execute order. We don't actually use that at all. We will use redeem cookie, but there's a add to sell order. We don't use that one. Remove sell order. You can look through. We don't actually use it. The vulnerable function was actually this one. So I think that you're required to implement this function, and we can take a look. Like I said, these challenges really weren't too hard. It was just hard to get set up. If you look at this function, it's external, so that means we can call it. I think you can call either external or public functions. And you pass in some address that isn't used, I guess, an address of from, a token ID, and some data that also I don't think is used. Can redeem token ID from. And so we have received a cookie from its owner, mark that it in the redeem mapping. But you can just call this. It doesn't do any sanity checks. So what you're going to do is just can redeem cookie is equal to 0 because we want the 0 cookie. And the from address is we're just going to set our own address. And it's returning something, but we don't really care. So we're going to set 0 to our address so that we can redeem the cookie, so that then we can call a function called redeem cookies. And this is where one of the checks happens. It just makes sure that we are the sender, which we already set, so that's true. And so then you're going to do cookie.approve, cookie.transfer, and then delete it. So to actually exploit this, it's pretty simple. We're just going to call this function, and then call this function with the index, and then we own the cookie. Like I said, really not too bad. So most of the script is the same as last time. I have the pwn tools. The challenge shuts down every half an hour. I got tired of copying over the lines, so all this does is it just generates this line right here, or these variables. Cool. We set up the RPC. We load the accounts. We just see what's in the values. Same as last time, there's a setup contract. We don't have the ABI for that, so you have to dump the code. You look through it, you see that it has a bunch of addresses. You pull the first two, and it's the cookie address and the cookie market. What I do is actually, I do one of these for loops, and I just print out the storage values, 50 of them, and I just try to make sense. And then I dump the storage at these two contracts, and I think cookie, where'd it go? Has these values saved in it, and so I saw cookie and E as values in the storage, so I knew that was the cookie contract. And I think within cookie market, I saw an address to the original cookie contract, so I was able to guess which one is which. So from that, we know what we have. Let me go back to the solve script. So we can compile all the code. We can create those objects now that we have the ABIs. And we can check the transaction counts, make sure everything makes sense. I just dumped the storage just for sanity checks. We can look at the cookie, see what the current ID is. And the current ID is 1, so that means one of the cookies was minted. Then we're going to mint our own cookie. I had a lot of trouble with this at first. It's very important that when you do functions.mint cookie, that you close this. If you call it like this, you get a very weird error that took a while to debug. But you get your transaction, you wait for the transaction, you get your receipt. It was valid. So then we're going to check. Sorry, I don't think we're minting a cookie. Oh, I think I mint a cookie just to see what happens, but we don't actually have to do that. My bad. What you need to do is redeem a cookie, and yes. So first you want to call this code. We're going to call the on ERC721 received code. We're just going to set our address. We're going to request cookie 0. This just happens to work. And so now after we call this function within the cookie market, it'll exist within mapping can redeem cookie. And then after that, we just redeem the cookie, cookie 0. And yeah, at that point, we're done. The cookie now belongs to our account. So you can go back to the netcat session and ask for the flag. It just gives it to you. And the very last one, we'll go pretty fast over this one. Bread bank. Again, we just get some files. Very similar. There's a netcat. We have 4 different things. So we have 3 different files. There's a pony token. I think it said it gave us a hint. You are the bank robbers, get all the pony tokens. Cool. So there's some new coin called pony token. We want to steal all of them. So that's what the pony token looks like. So it's initially created with some amount, and the amount belongs to the sender. There's a bread bank and a bank pair. What's going to happen is when you can create this thing called a deposit token. So you're going to pass it that pony token and the amount. So you want to see, first you need to see how many pony tokens exist. Then you're going to call it with this. It's going to do some sanity checks. Then it's going to create this thing called a deposit token, which is just this. It's just an address, the underlying, and some amount. Basically, it's like a one-to-one swap, I guess. And so yeah, it'll mint this bank token for you, and then later you can do this calculate rewards. You don't actually have to. You don't have to do issue rewards. All that stuff is just extra. You can call redeem with the bank token and how much you would like, and the bank will give you the pony tokens corresponding to how much was initially deposited. So what's really strange about this challenge and makes it super easy is for some reason you're allowed to create a deposit token with all of the tokens just by default. So I'm not sure if this was an error or if it was the intended thing, but it specifically says, it asks pony token, what is the balance of my address? And for some reason, the balance right off the bat is all of the pony tokens belong to the bank, and you're allowed to just claim those. And so you just call create deposit token with the pony token, all of them, it was like 2 trillion or something like that. It'll give you back a bank pair token. It was a little bit, actually, I'll talk about this. It was a little bit tricky to actually get the return value, because you don't actually just get a return value from an Ethereum contract call. You have to actually get it from the logs, which took a while to figure out. But apparently in the logs, there's log data, there's log topics. I think I have it down here. Yeah, so this is what the response of a receipt looks like. So you have your logs. What's strange is it has these topics. It turns out this is like the hash of the function signature of the thing you called, of the thing that emits a log. And then this is, if the log event fields are called indexed, I think, it'll tell you what it is. I think this was amount, and this was like one of the addresses, and then this is also another value. Oh no, this was the amount here. I think this is like 2 trillion or something like that. Very confusing stuff, but eventually you find out that this is the address that emitted the event, which is what we want. Phew. So you take that address, the bank pair address, so this is that bank pair, then you can create a contract from it, although I don't think you actually need to do that. You give the bank pair address token back to the bread bank to redeem it. At this point, it'll transfer all of those tokens to your address, and then you can go back to Netcat, say, hey, I have all the tokens, and you get the flag. So, like I said, at the end, very simple challenges. It takes a while to kind of set up and wrap your head around everything, but the actual exploitation was pretty simple. Cool. The next challenge is the Carol Corruptor. So let's go to crypto Carol. Cool. So this one took me quite a while, and the code is probably not going to be amazing. There were two things that, actually, let's run it first. Cool. I think that they also give you the code, but if you look at this, so there's a bunch of random bytes that are given to us. We have 3 options. We can corrupt Carol, stop the machine, or quit. Corrupt Carol, I spent a lot of time on this. I thought we were supposed to be using these random 4 bytes. It turns out we're not. It was just a false flag. We can also stop the machine. It'll ask for a secret. It says, oh, your carols are forever corrupted, or we can quit. We're given the source code. So we take a look. It creates something called a Krampto. It'll do secret is equal to nothing, generate secret. This is where the interesting stuff happens. So for I in range 31, get ran bits 640. So this is 32 times 20. Cool, is this enough? Maybe, maybe not. And so this comment is left here because it's somewhat well known that for Python I think it's mezzanine twister, something like that. If you have 624 4-bit integers from a random number generator in Python, you can compute the internal state, and from there you're able to guess the next random numbers in the sequence. And so normally on a CTF challenge they give you 624, but on this one, if you actually go through, they're giving us 620. So we only have 620, we're 4 short. And so the tool that I normally use just doesn't work. So that's why I was playing with the Corruptor. I was trying to get maybe these random bytes or something like that. But it turns out you can actually get this to work with less than 624, which is pretty cool. So what we're going to do is we're going to read in all these bytes. When it does, oops, let me go back. When it does get ran bytes of a larger number, basically it just means that this is the first 32 bits, this is the second 32 bits, third, etc. So you just have to do some integer math to get them in the correct order. Cool. So what we're going to do is we're going to predict, we're going to sync up with this random number generator, because the next call is going to call a bunch of bits, and then it's going to set secret to whatever the result of this is. But if we remember, like I said, the way this happens is it actually, this is the first call to random, this is the second call to random, etc. So the first 32 bits is actually the next call after the 620 call. So this is actually 621. It's not exactly, because it's being cast as an integer, not as a hex. So it won't be perfect, but like roughly it's going to be over here in the 2048 bits. So to do that, there's a bunch of tools. The ones that I ended up using were a tool called Untwister, which I found somewhere on GitHub. Ooh, I probably should have cited. Eventually, searching through GitHub, there's a bunch of people that have copied this code, and it just loads Z3, and what you can do is just give it a bunch of values, and within Z3, it'll try to calculate what the initial state was, and then give you a random instance at that state. What's cool about this one is, so you actually, when you do submit, let me go back to the solve script. When you actually call submit, you're supposed to call it with the binary representation of the 32-bit value, and that's because you're actually allowed to submit question marks within those 32-bit ints, which is pretty cool. So if you only had like the start of a random 32-bit integer, you could still use that tool, or this tool for that. So called Untwister. So anyways, we're just gonna parse, going back up. So we're gonna, so the next part of the exploit is we do that, but then we have to go backwards. I couldn't figure out an easy way to go backwards, but there's another tool called extend mt 19937 predictor. This tool allows you to backtrack. And so what I'll do is I'll sync up the result of the untwister with extend mt, and then I'll just go backwards and then calculate the secret that generates the flag. So like I said, we're just going to get the lines from the program. It's each one of these. We're going to parse out all the individual 32-bit integers. I just do it like that. And from there, we're going to have a giant array of 620 integers. Then we're going to use the untwister code to submit the 620. Then we submit 4 unknowns. Then we ask the untwister Z3 to get us an instance of random. From there, we're going to sync up that random with extend mt. I do that by just calling it 624 times, setting it. Then I ask it to backtrack. And then I ask it to backtrack again. And then at this point, it is now in sync with the original server rand. And so I can ask it this call, and it'll give me the secret. So pretty fun challenge. It's good to know that you can do it with less than 624. I did not solve the rest of the crypto challenges. Cool. For Misc, there's the default one. There's jump onto Discord. The next challenge was Krampus Bet. This was a pretty neat C++ challenge. It was under the Misc category. It turns out this is a pretty well-known puzzle. Basically, there's going to be a deck of cards, and through some manipulation, 2 people have to team together without talking and solve the challenge. and the challenge is to identify the position of a specific card. So to do this, we're going to program two different bots. Both these bots are going to be programmed in C++. So like I said, there's two bots. The first bot is going to execute once. The second bot executes up to 26 times. And like I said, the goal is the two of them want to work together such that they can identify the position of a hidden card. So the first bot is going to go into a room. They're going to see all 52 cards face up, and they're allowed to make one swap. The cards that are face up are in a random order, but the bot doesn't know which card the next bot has to search for. He just gets to make one random swap. The second bot, the first bot will leave the room, and then the first bot is out of the game. The second bot goes into the room, but before he goes into the room, all the cards are going to be flipped down, so they're face down. The bot's going to be told, you need to find the fifth card out of 52, or something like that, card number 5, and he's allowed to guess 26 times. So at first this seems impossible for this to reliably work, but it turns out, like I said, this is a well-known puzzle. There's a solution. I just Googled around and I found it pretty quickly, because at first I thought this was impossible, and it seems strange that this was in Misc and not Pwn. But it turns out the trick is to generate cycles. So what the second bot will do is, if it's looking for 5, it'll start at index 5, see what card is there. If it's not the card it's looking for, it'll go to the index specified on that card. So for example, if it's a 9, it'll jump to index 9, it'll check the card there. If it's not that card, maybe 9 will say 3, it'll jump to 3, and etc. And the idea, or the trick is, in a 52 card deck, the very longest cycle could be 52 long. For example, if 2 pointed to 3, 3 pointed to 4, 4 pointed to 5, etc. But since player 1 gets to see all the cards and they're allowed to make one swap, they can always break up that cycle such that the max cycle is 26. And so that's what you end up programming. So if we look at the code, it's under bet, main.cpp. Get rid of all this stuff. We have to implement those two functions. So this is the code for the first bot. You netcat to the server, it just asks for the raw C++ code, so you just send it this. The first bot's just going to go through, it's going to calculate the cycle lengths. If it finds a cycle that's over 26, it just cuts that cycle in half. And you cut a cycle in half by just swapping the endpoints. And then the second bot is just going to go through. I'm not sure if I clarified this, but the second bot, all the cards are face down at first, but every time it makes a guess, that card becomes face up. So at start, all 52 cards are down, it's going to guess a bunch, and one by one, they're going to be face up, but it only gets 26 guesses. So at the start, I just do a sanity check real quick. I check all the cards. If the card we're looking for is flipped up, we just quickly return that. If not, we cycle through on our little chain, max of 26, and eventually we'll get to the card we're looking for. So, fun little puzzle. Manipulated Christmas. This was a kind of guessy challenge. Basically, we're given a file. We're given 3 files: X-MAS, flag, a zip file, and a keypass file. And we're given a hint. We're told start with the image, then the zip, then the keypass. Not your typical kind of stenography. Think like an attacker. We get an initial password. For this, a lot of people in the Discord were, I wouldn't say complaining, but very lost, so I kind of put this challenge off for a bit, but eventually I took a look at it. Oops. You're given this image. I ran through the generic stenography tools, and there wasn't too much that was obvious, but a couple of the tools reported that there was extra data at the end. And so what you can do is there's these tools that extend JPEGs. There's one called mod size, which funny enough actually references a previous XCTF challenge, or X-MAS CTF challenge. But you can use this. Basically it means that the JPEG file can have a bunch of data, but in the JPEG header it can say it has a specific width and height that's smaller than the amount of data that's actually contained in it. And so you can use it to hide information. So basically you just use that tool, you call it with the parameters. I think I extended the height by like 200 pixels and it just popped out. So we get a first flag. You can use this to decrypt the zip file. Within the zip file there's a file called pass.txt. At this point I got stuck. I thought you were supposed to use that to open up the key file, So you can either use the CLI or there's like a Mac Pass sort of app. I was trying a bunch of different combinations to get that to work. It didn't. I actually reached out to the challenge author. I wasn't sure if I was just using KeyPass wrong or if, I don't know, I was just doing something silly. He was nice enough to give a sanity check, and he said that none of the flags or the keys that were given don't open this key file. And so instead we're supposed to brute force it. He didn't say that, but obviously there's nothing else you can do at that point. So you can use, there's a tool, I think it's like KeyPass to John or something like that. You can use that and it'll dump out the hash, which looks like this. You can then take this and just give it to Hashcat with the Rocky library, and a password pops out. I think the password was Dracula. Once you do that, in the KeyPass, there's only one password. And it says something like, we managed to extract the data, but I can't figure out what it is. The attacker said it should be something easy. We only know that he likes some good cooked fish. So this kind of refers to blowfish. And we're given this ciphertext. And this is stuff that came from before. Actually, I think this was in the file too. And this came from before. I think the file looked like this, with no Christmas joy. Cool. So at this point, I figured it was blowfish, but again, it wasn't that simple. I just couldn't get it to work for the longest time. I tried every combination. We had these 3 values, but these both base 64 decode into 2 other values. This was like Christmas or something like that. Yeah, Christmas for joy. Different combinations of key and IV, like these just don't make sense for keys. They're not the right 8 or 16 bytes. So again, I reached out to the challenge author for another sanity hint after spending quite a few hours, and they were nice enough to just say, I just wanted to know if it was actually blowfish. There's also a fish cipher, all that stuff, and they said that blowfish was the correct cipher. So I kept trying. It turns out, like I said, I was brute forcing over every mode, and trying every key and IV. What's strange is, manipulated, Python 3. I took a closer look at what was actually being popped out, and if you actually look, you see an HTTPS, and over here you see a paste bin. And so this is mode 1, which is ECB, and this is CBC. So I'm not really sure what's going on, but I think the challenge author said that they use some online tool for generating blowfish ciphers. I'm guessing that it pads the initial password if it's not a multiple of 8 in some way that's different than Python's default implementation. But anyways, we get the paste bin link. You go there, it asks for a password. You give it the other password, I think Christmas for joy or the base 64 of that. Or it might have been this one actually. And then you get the flag out. So kind of a guessy challenge, but the JPEG trick was definitely neat. Next, there were 4 programming challenges. This was definitely, I think, my favorite section. So all the challenges kind of had like a neat little trick to them. I'm not going to go over the code too much. I don't think it's too insightful, but I just want to talk about the core idea of each challenge. So the first one, it's kind of a matrix rotation problem, or a Rubik's Cube problem. So you're given this array, and the array is going to rotate on any number of row and columns, but it's only going to rotate on either rows or only columns by some amount. And your job is to figure out how many rotations are necessary to take it back to the initial state. And it's very nice that it's either rows or columns, which makes it pretty simple. So basically you're just going to iterate over the top one or the side one, and you're going to see how far away it is from the default state. So really not too bad. I mean, we can look at the code, but I don't think it's too exciting. This was, I call it Rubik's one. Cool. So first I check if it's either a row or a column shift, and then from there, I mean, this is all the code. If it's a row or if it's a column, if it's a row shift, I just calculate the minimum, because you can rotate it either way, either each individual row to the left or to the right. So you just need to see which one's shorter, and then the same for the columns. Then you add it up, and then I just had a bunch of test cases. And from there you count, and there's formatting and stuff, but that was the entire challenge. Really wasn't too bad. Infested Cellar was nice. I think it had a fun solution. Basically, it's like a sort of like a min-max problem. basically there's going to be n barrels, and you're going to have a bunch of spray that kills insects in the barrels. And so there's a variable amount of insects in each barrel, and you have two different types of sprays. You have a strong spray and a weak spray. I think for most of the challenges, the strong spray does like 5 damage, so it'll kill 5 insects, and like the weak one does like 2 or 3 damage. And so your goal, and each spray can only be used once per day. And your goal is to figure out how many days until you can kill all the insects. So, I think the trick for this challenge was, it's pretty difficult to calculate the number of days required to do this, but it's not too hard to guess a day and see if it's possible. So like I said, it's hard to figure out the exact day, but it's easier to ask, is it possible to do this in 5 days? So it's kind of like a one-way function. And so for my algorithm, basically I just say, hey, is it possible to do it in 10 days? And I'm going to do a binary search based off of that information. And the reason it's easy to calculate, is it possible to do it in X days? Because you know that at a minimum, there's as many sprays as there are barrels. So you're at least going to do the minimum amount of damage every single day. And at that point, you're just trying to allocate your high damage sprays so that you can kill all the bugs. And so basically just have to make sure you have enough strong spray to kill everything. And it's really not too bad of code to do. This is possible in days. This is the function. So again, really not too bad. And then from there, you just do a binary search. So you find some lower bound, some higher bound. I think low bound is like, what if I kill everything with just the strong spray? And high bound is, what if I have to kill the strongest thing with just weak spray? You could probably restrict these bounds more, but from that point, you just do a binary search. So you take the midpoint. We can say, let's say this is a 0, this is 100. So days would be 50. If you're able to do it in 50 days, the condition that you're trying to find is where it's possible to do it in n days, but it's not possible to do it in n-1 days. So then you know you have the minimum. So if we do 0, 100, 50, let's say it is possible on 50, we know the answer is not going to be higher than 50. So then we set the low bound to 0, we keep it at 0, and we set the high bound to 50. We know the answer is somewhere between 0 and 50. And so you can do this kind of logarithmic binary search, and eventually you'll find the answer. So pretty fun challenge. Elven puzzles. This was a continuation of the Rubik's Cube problem. At this point, instead, you're given a grid that is like a pure grid from 0 to n squared, and they're going to perform these moves, and you need to figure out how many times this set of moves needs to be repeated before it goes back to its initial state. What's tricky is that the limits are pretty high. So your board could be 1,000 by 1,000, which is pretty huge, and you could have 25,000 moves. And they kind of hint at this, that it could be huge, is because your answer should be computed modulo 1 billion. So you know it's going to be huge. You can't just do the naive solution. So my trick for this one, this is Rubik's 2. Well, this will work. So let's say we had 0, 1, 2, 3, 4, 5, 6, 7, 8. Let's say this is our initial board. What I will do is I'll run over all the moves once on the board, and from there I kind of have like I guess it's kind of like a Markov chain, maybe, or a state machine. Let's say the thing that's here after one full cycle moves to here. So we know that anything that's in this square, after doing one cycle, will end up in this square. And let's say after anything that was in this square will eventually move to, let's say, this square, and then let's say it goes back to the square. So we know that this 8 to this to here has a cycle of 3. And so what I'm going to do is, let's ignore this. I'm going to try to calculate the cycle lengths for every individual spot. And so let's say like this one, let's say it goes from here to here to here to here. So we also know it has a cycle of 3. And basically just kind of go through and do that. So you only have to do one iteration. From there you generate this map. You know the froms and the twos. You just loop through and find the group size of each individual spot. So let's say it looks like, I don't know, this. Something like that. So we're saying this one never moves. Maybe this one moves here and then back or something. Actually, that's not possible, but maybe like this. It goes up and down. I don't think that's possible either, but we'll just ignore that. you know, it's doing some cycle of group 4, some cycle of length 6, and actually that means there would be 6 of them, so this is a really bad example, but anyways, you'll calculate the cycle lengths of all of them, and from that point you can do a least common multiple. So you know it takes 6 iterations before this square makes it back home to where it belongs. You know, it takes 3 for this one, so you just need to figure out when those cycles align. And so you can just do LCM. So I think the LCM for this one would be 12. So yeah, you take all these, you would sort it, you would remove the duplicates, and yeah, you get an LCM of 12 because all of these evenly divide 12. So pretty fun challenge. I tried to do it, like try to be clever, like if you have a horizontal followed by a vertical followed by a horizontal, but that just got way too complex too fast. The last one was Elven words. My solution for this was a little nasty, but basically what we have is we're going to have a dictionary of words. When you actually do the netcat, usually it's about between 300 and 600 words, and you can generate any combination, you can generate new words from any combination of the previous words. And sometimes the words do duplicate, or you're given duplicates, and then you're allowed to use those duplicates. And your job is to essentially find words that repeat a certain letter many times. And you want to generate, there's 2 different things you want to figure out. You want to figure out the longest word that generates, that is a word that has a lot of a single repeating character. And you want to figure out, that's the maximum length. You also want to figure out a word that has a lot of small words built up that repeat a single character. And so the exact definition of what it means to repeat a lot is you want this thing called an original word. And so they say an original word is a word that contains more than 50%, it just means more than 50% of the word is composed of a single letter. Cool. After the challenge was finished, someone in chat or Discord said that this was a knapsack problem, which after reading it, this is exactly what it was. I wish I had seen this earlier, but basically to solve it, again, I don't think looking at the code is going to be that insightful. It's like 400 lines, I think. This took me the better part of a day. But basically, you sort it, you take all your letters, or sorry, you take all your initial words. I generate something I call letter bins. And from there, it kind of looks like this. So I take all the words that have a U in them, and I generate this map structure that kind of looks like this. And so this is the ratio of the letter that I'm interested in to non-letters. This is the length of the word. This is what the actual word was. And then I generate something called an offset, or it's kind of like a budget. This one has a budget of 1. I'll explain it on this one. So to be an original word, it has to be bigger than 50%. But as you're building the original words, you just need one word that's over 50%. And then if you keep adding words that have a 50% ratio, you're always guaranteed it's going to be more than 50% combined. So what usually happens is you're going to have like, let's say you had a word that was like AAA. From this point, you can add like a B, and it's still greater than 50%. And you could definitely add a bunch of ABs, BAs, for example, because these are at 50%. So you know you're never going to go under that 50% limit. So anyways, from these I calculate this thing called a budget. So this is 50%, and let's say I'm trying to build a long word with D's. This is 50% right here. It means I have an additional 1, 2, 3, 4, 5, 6, 7, 8. 8 non-Ds can be included, so I call it my budget of 8. But anyways, like I said, there were 2 things you need to solve for. You need to find the longest, so built up of a lot of characters, and also the word that's built up of the most total subwords. So usually for that one, you usually want a bunch of short letters. One of them you can do just a pretty simple greedy algorithm. So I think it was maximum count. So the number of words. You can do a greedy algorithm where, again, you're just kind of looking for words that have a very favorable, I call it offset, but budget. And you can just kind of sort and then pick those out. Like I said, greedy solution. I think to really understand it's just best to write the code and play with it. The other one, as far as I can tell, wasn't greedy. I'm curious to see other people's solutions. But to find the maximum length of a single word, I think at the end you do kind of have to brute force it. I think you can get pretty far, but at the end I ended up building this like tree-like structure that would test all possibilities. So that grows factorially, and so at some of the later rounds within the challenge, it just wasn't possible to do. So at this point I kind of cheated. Basically I implemented a greedy algorithm where I just kind of guessed what would be the best words to include, and then once it got to a size I was able to brute force, then I would go back and kind of brute force the last remaining budget. And so I saw on my Mac I was able to brute force when children were 13 or below, or there's 13 children or less, which is, it isn't, I'm not actually doing 13 factorial. For example, I could have a budget of 10 and one of the words could eat up 8 of my budget. And so at that point, I would only be able to use words that have budget of 2, or I can only fit budget of 2 words. It worked. So like I said, this script didn't work that often when I connected to remote. It actually worked on the second try, but I forgot this interactive. So it said I won, but I forgot to record the flag, which was a bummer. So instead of spending more time on it, I just put in a very slow for loop with a nice sleep, and I just let it run in the background. I don't think I slowed the server down, and it's just text anyways. But after I think maybe like 100 rounds, eventually it popped out. Yeah, it's a fun challenge. I bet there's a better way to do it, so I'm definitely excited to hear other people's solutions. Last 2 challenges. The second to last one was a Minecraft challenge. I don't play I don't really play Minecraft. I played it before, so this challenge was a little bit confusing to me. I've never set up Forge, and I've never used a custom NPC, so I think for me the hardest part was just getting everything set up. At first I didn't install Forge, I only installed the NPC files that were given, and so the world, you can still go into the world, it just didn't really make any sense. There was like a chest and it only had a block in it or something, but anyways, once you get everything set up, there's an NPC there, and you can talk to the NPC, and he will give you 2 scripts. Let's see if we can jump into the world in the background. While this is loading though, we can look at what the actual scripts were. Rev, Minecraft, Gimi. Close this, don't need that. Don't need that either. So like I said, the NPC will give us these 2 scripts. You just have to interact with it. The first script is not too exciting. I think this is just like default NPC template. Yeah, nothing really happening. The only thing exciting is at the very bottom. So when it inits, it'll say, the NPC will say this. And then anytime a player says something, so we're the player, it'll just say Roger. It's going to take what you said and save it to some global variable along with this R key. And so let's see if Minecraft is running. Cool. I just want to show what the computer looks like once it loads. There we go. So we have, this is the NPC, and so you're able to interact with him. And there's this like computer-like thing behind him. And so what he's going to do is he's going to set these blocks on and off, and it's going to perform some sort of calculation. I feel like if I knew Minecraft better, I could reverse this, but I'm really not sure what all these things do. But at the very end, down here, he's then able to read the output of it, and that's the encryption algorithm. And so you can kind of see this is the output. We have 1, 2, 3, 4, 5, 6, 7. So it's 4, 1, 2, 3, 4 groups of 7. So it's pretty cool. Let's see if we can exit this. So how he's actually doing that is this is his second script. Like so I said, he had 2 scripts. He can set blocks in the world globally, and so he's going to set those initial ones to redstone or wool. So I think that means on and off, based off of the data that you say. And so the idea is if you say the flag, he will encrypt it, and then he's going to compare against known ciphertext, which is here. And if they're equal, then obviously you win. What makes it a little bit tricky is there's this R key thing, and so every time you encrypt it, the encryption happens character by character, and every time this R key is updated. So you can't just start in the middle. It's also a little bit frustrating because Minecraft, I guess, those circuits are a little bit slow, and so you have to wait a certain number of clock cycles, so it only happens like once every couple of seconds. So testing the flag is just very slow. Like I said, I think if you knew Minecraft, you could just look at the circuit, write that in Python, and then just solve it super quick. Instead, I'd want to deal with that. I modified his script so that he brute forces it for me. So he's just very standard, just brute forcing. We know what the ciphertext is. It goes character by character. I think it outputs 4 characters at a time. And so what I do is I just start with the known base. So X-MAS, and I guess this, and then I guess, X-MAS A, X-MAS B, X-MAS C, and I see if it matches, 4 times up to here. 4 times the number of characters I gave it. Eventually it gets really slow. Each character takes a couple of seconds, and so if you're going through, guessing 1 out of 1, it's just way too slow. So eventually I updated it so it saves the R key, and so then I can just start here and brute force it. And eventually, I forget what it was like reverse or encryption or something like that. Hardware encryption, I think, was the key. And eventually you build this out. So pretty fun challenge. Then the last one, I was very dumb when I started this challenge. So there's not much here. If you look at the headers, the source code, there isn't that much going on. I tried, robots and sitemap for a quick minute, but there just wasn't much going on. Anyways, you start playing with the URL, and you see that this works. So 1 + 1, it gives you 2, bell. Like I said, there were 3 of these things, and you can access them by ID. And so we can see 1 + 1 is also equal to 2, and you get the same one back. What was super weird and threw me off was this. So you can type in min 1, 2, and you get the minimum. And at this point, I had just assumed it was Python. Some sort of, Python eval or exec or, I don't know, template injection. Something was going on. So I played with this for a long time. This also worked, which was confusing me. Eventually, like an hour later, I found out it was actually a SQL injection. It wasn't Python. I forget how I figured that out, but once I figured it out, you just load it into SQL map and start dumping the database. If we look at what we actually got, so yeah, this was the request. You just save this. I think I had a proxy one burp. I saved that request to a text file, then I run SQL map on it. Eventually you'll dump out the database. There really isn't that much in the database, which was also very confusing. I assumed once I saw SQL map was working, you'd just be able to exfil the flag. But there isn't anything in the database. After spending a lot of time reading to see if there was anything else that worked, I came to the realization that, actually, let me back up. The only things in the database were this table of elves. There were 3 elves, and they all had a ID and this data thing. And it was just this like base 64 blob. And that was it. I decoded this, and I saw some you can see the text inside, packing gifts and the name. Eventually, after searching through the database for longer than I'd like to admit, I eventually found out that these are pickle objects. And then the second insight was you can do union select and return arbitrary data, like a hard-coded data. So what we're going to do is, the program gets really mad, like if you do for or something like that, which doesn't exist, or if you return multiple, if you were to do 1 or 1 = 1, for example, if more than 1 gets returned, it gets mad. It doesn't give you an error message, it just says internal server error. So if you do one that doesn't exist, or you do union select, so you're going to add an additional entry, a hard-coded pickle object, this will work. So at first I tested it with the original pickle object. I got that working. And then I created my own pickle object. And so I'm not sure if it still needed the same structure, so I just included it anyways. There was name and activity. But then we give it the command. From here you see I'm just calling out to some webhook site and then catting the flag. I think I did ls first. I saw that there was a flag in the directory, and then I do cat flag base64, and then I was able to read it. Yeah, that was the challenge. Anyways, I think that's all the challenges. Again, had a lot of fun with the CTF, a lot of cool stuff. It's been a fun 5 days, and yeah, take care. Bye.